Hey, well, welcome back, everyone, to the second half of our symposium. This will be a two-part talk. I'll do the first half to talk about just some thoughts on how to architect scalable applications for many core processors, going through the different levels of parallelism and just some of the ideas, some of the gotchas, some of the problems that you may encounter. And then I'll turn over the talk to Jerry Batista from Intel, who will talk about connected visual computing, which is an exciting area of combination of graphics and immersive environments. So he'll be able to show you some of the work that's going on at Intel and in the community in general about some of the exciting new applications that you can do with many core processors and with the enhanced computing power that these processors will deliver to us over the next 10 years or so. So I'm going to start here, and I'm going to give you sort of a different flavor of the free lunch is over concept. As an application person, to me it's all about, what's the performance I can get, what's the number of computations I can do on a processor, same amount of time, how much more complicated can I make my application to run and still finish within a reasonable amount of time, which is user-friendly or meets deadlines and things like that. And in the past, if I had a code which perhaps, sequential code which wasn't written very well, but, satisfied the computations I needed to do and met the deadlines I needed, I was sort of guaranteed, as I planned out my application over the next, 2 years or 5 years or 10 years, that every couple of years I'd either be able to run twice as fast or do twice as much work, sort of regardless of how well I had written my sequential code, because the clock speeds would get faster. Okay? So if I had been sort of naive and implemented a bubble sort, the n-squared operations would run twice as fast next year, and I'd be able to do a bigger problem. That's not the case with parallel computing, right, and parallel codes. If I write a bad parallel code, it's not going to scale when the number of cores increase in 2 years, and so my code's not going to run faster. So I can't write bad parallel code and still expect to be able to ride the wave of increased number of cores on a processor. And there are a wide variety of reasons why a parallel code might not scale, even though the number of cores have increased. And in this graphic, we can see that, often a parallel code, as the number of cores increases from maybe 1 to 2 and 2 to 4, it'll continue to increase. But at some point, you'll reach some bottleneck in the code, and the code will no longer improve in performance as the number of cores increase. And in fact, as the number of cores increases beyond a certain limit, you may actually get a performance decrease, and performance may actually diminish. And this can be for a variety of reasons. The most simplest one is perhaps that I took my code and I decided, well, I've got 2 things to do in this code, or I imagined I only had 2 things to do, so I simply wrote a code that has 2 tasks. And, I simply set those 2 tasks out to work concurrently. And so, when I had 2 cores in the machine, I got twice the performance because each task had its own core, its own resources, so they both were able to execute concurrently, and the code completed in half the time. But now, of course, I get a processor in 2 years that has 4 cores, but my code still only has 2 things to do concurrently, and so even though I have 4 cores now, my code still only gets a speed up of 2 and not 4, and so now I have to go in and re-architect my code and increase the amount of parallelism so I can exploit the 4 cores instead of only the 2 cores. And the bottlenecks can be other ways. It could be maybe I have a lot of parallelism in the code so I can exploit as many cores as I get delivered, but if the concurrent tasks are synchronizing or communicating and that causes them to have to wait on one another, then the number of tasks that are actually concurrently executing at any one time might be a small fraction of the total that I've exposed. And so there, as the number of cores increases beyond the number of active tasks, the problem will simply stop scaling. And so I've got to go in now and, again, re-architect and remove and diminish the synchronization bottlenecks or the communication bottlenecks that I put into my code. So if you don't want to have to rewrite your code, every few years as the number of cores increases, you really need to start thinking about, how do I architect the code so it's general and it's scalable to a large number of cores so that I can continue to ride the wave as the processors increase their computing power. So I don't want to scare anybody, but it's not quite as easy as it used to be. So the agenda of the talk is how to think about different levels of parallelism, and I'll go through some definitions and just some different general models, how to think about parallel algorithms, and then just some optimization techniques and some things to think about as you write your codes and some of the bottlenecks that may be not so obvious. And I'll hopefully be able to tie many things back to David's talk. He talked a lot about how we'll implement many of the different models of parallel programming and some of the features that we'll deliver. And I have some examples in the talk, which you'll be able to see some specific examples of those things. Okay, so the first thing you really have to decide is, do you need parallelism at all, right? There are many applications today that, run in a reasonable amount of time on a single core. They don't really need to do more computing, or even if they need to do more computing, you can still get that done in a reasonable amount of time on a single core. And if that's the case, and the problem is working fine today and to what you expect to put into the application tomorrow, then you don't really need to worry about parallel computing, and you can go on just the way you have things done. If you do need parallelism, or you do need to do more tomorrow than you're doing today, then there's sort of two forms at this highest level, right? One is what's known as throughput computing, and one's known as what I refer to as capability computing. So in the throughput case, you have n instances of a problem, and you need to execute those n instances as fast as possible. So two examples of this would be in the construction of an animated film. You've done the design, you've got the film done, and now you simply want to generate the frames of the film. And so you want to generate each frame separately. They're separate instances of the same problem. You need to do 10,000 of them or 100,000 of them, or depending on the size of your film. So you simply get one processor per frame. You execute that frame. When that frame's done on the processor, you send in another frame to render, and you get the film done overnight on a large cluster. Another example would be portfolio simulations in the financial system. I have a set portfolio, or I want to look at a variety of parameters as they change over time for a given set of financial instruments. And so I simply send out instances of the same problem in order to compute what the expected value of those different portfolios under the different conditions would be. And again, as each processor finishes its current simulation, it asks for another one. So in this model, at the highest level, I simply need to write some sort of master-client relationship in which the master sends out problem instances to the clients, and the code can be sequential in each of the clients. The capability problem is the reverse of that, in which I have one instance of a big problem, and I need to get it done in time t. So examples of this, where I have a single problem, it's very complex, and I need to solve it in a certain amount of time. Three examples of this would be the director frame. So there's actually a corollary to the throughput example in films. And this is where I need to design a single frame so the director can make a decision. I want that done as quickly as possible. Intelligent avatars in a game, right? I want to make my avatar smarter and more responsive to make the game more realistic. And so here, again, I got a single problem, the intelligence of a single avatar, and I want to accelerate that so the avatar can be more challenging. Speech recognition is another example. I have a receptionist, or I have some sort of automatic input device where I want to be able to recognize what the speaker is talking about. And of course, I want that to be as responsive as possible, to be as intelligent and responsive as possible. And so I want to solve that single problem of recognizing this particular person's speech in as fast as time as possible. Okay, so throughput computing, as I've said a little bit here, at the highest level, I need some script or just some general piece of code which goes through the parameters that I want to model, or the different instances of the problems that I need to compute, and simply sends out to each of the cores or each of the processors that I have in my cluster. And maybe there's some sort of result that comes back, that the master then has to gather. But this is a fairly, embarrassingly parallel problem. The highest level of code, or where the parallelism is simply at the level at which problems are sent out to be computed. And the easiest way, of course, here to decrease the processor time is simply to get more processors or more cores and simply have more workers. So it's fairly simple. And besides parallelizing at the top level, which distributes the work, maybe I'm okay with working with simply sequential workers, and so I don't really need to change the code for the worker threads. And this is okay, but there are two gotchas, and a lot of people don't realize this. One problem is that if the worker threads aren't balanced, right? So I've got a lot of worker threads, all that take, let's say, a couple of seconds or a couple of minutes, and I've got a couple of instances of the problems that take hours, okay? And so if I don't parallelize the worker thread now, all the quick instances will come back quickly. The long instances will stay out there for an hour or two computing, and in the end, I get my final results after a few hours with only one or two processors working, and the rest of my farm, of course, stays idle while these two long workers compute. So I can stick with the sequential code. I don't have to parallelize the worker threads as long as my problem is relatively balanced, and I can exploit all the hardware I've bought. The other sort of gotcha on throughput computing is if the single problem doesn't fit on a single computing element, okay? So I've got a problem. The instances of the problems maybe, let's say, take 8 gigabytes of memory, and so, they run fine on a single core, single processor, where there's 8 gigabytes in the system. But now if I want to take the 8 cores I have and run 8 problems, of course, they no longer fit, right? So I can't use the 8 cores on a single processor because each of them only has 1/8 of the memory. And so I end up running only one core because I need 8 times the memory, okay? So that's another gotcha of throughput computing. And if you have a problem of that ilk, you do need to go in and parallelize the worker threads. Okay, so capability computing, again, this is a case where I've got a large complex problem. I want to use all the hardware resources that I have in order to solve it. So here I do have to write parallel code. I do have to take my what was sequential in nature before and now parallelize it. Again, here are just two examples of capability problems. Of course, this is usually the purview of high-performance computing. So two examples, though, would be, again, the rendering of a short sequence of movie frames quickly and accurately so that we can get the expensive director busy and that we can get enough accuracy in the frames for him to make the right decision. And then, of course, from the games world, making the opponents in a game, more faster, more skillful, better accuracy, more intelligent. That will all take more computing power. And so, I probably want to bring all the resources I have in my processor or in my game box to bear on solving that problem. Now, some of the challenges of capability computing, and probably the biggest one, is that the problem is always as big as the machine, right? A long time ago, I used to work at Lawrence Livermore National Laboratory, and I made the mistake early on in asking the scientist, well, how big was this problem? And he turned around and he said, well, how big is your computer? Okay. If I have, for example, in the games, and I want to make the opponents in the games, I can always make them faster, more intelligent, more skillful, carry more weapons and things like that. And so, you can imagine, more AI in those processes. So, regardless of how big I make my, game box or whatever, I can probably always, find ways to use that computing power to make the game more challenging. Okay. So it's always a case in these capability problems that I really need to find ways to use all the resources. And so I really need to be able to think about, how do I parallelize my program to use all the resources that I have? To do that, I've got to sort of solve 3 problems. I've got to be able to decompose either by task or data so that I can use the actual instruction pipelines that are available on the processors to, compute more tasks or to consume or process more data. And since these are parallel tasks, there's probably going to be some communication of shared values, right? So I've got to be able to communicate those shared values in my code and to minimize the contention among those shared values. And also I want to minimize the time the processes wait for shared values, because while they wait, of course, they're not advancing and resources are wasted. And besides just simply sending the data or sending the values between the tasks, I need to be able to synchronize access to shared values as well. And so I, of course, want to minimize the number of synchronization points I have. I also want to minimize the contention for those synchronization points so processes don't wait to be able to access the shared values they need. And since I'm using all the resources in a machine, those include not just only the, the cores, right, the instruction pipelines themselves, but this also includes the memory subsystems and the communication bandwidths. It can include the I/O, depending on, exactly what the nature of the application is. And so there are many critical resources in a system, and as an application programmer, I've got to be able to realize what is the critical resource, right? Is it compute bound, then it'll be the cores, right? It'll be the instruction pipeline. But if it's memory bound, then either it'll be the size of the memory, maybe the size of the L1 or the L2 cache. So I need to write my application in order to maximize that resource. It may be simply loads and stores to the main memory, in which case I need to sort of write my code so I optimize for the bandwidth of the available system. So in these capability problems, as you design your parallel application, you have to understand exactly what the nature of it is and what will be the critical bounding resource within the hardware, and write your code to optimize for that. Okay, so David touched on this a little bit. I want enough parallelism to keep the machine busy or to saturate the critical resource, but I don't want too much, right? If I get too much parallelism, then I get contention. I get things that are sort of blocked. It's like having too many cars on the road. I want enough cars on the road so that I'm using all the lanes and transporting the most number of goods. But if I get too many cars on the roads, then I get traffic jams and bottlenecks, and then the whole system sort of breaks down. So designing, thinking about your application on where the right level of parallelism is perhaps the most important thing for you to sort of decide originally. Okay, so too much parallelism may increase communication and synchronization costs, right? I may just create big bottlenecks as processes spin, waiting for the resources or waiting for their turn. They're consuming resources, they're consuming bandwidth, they're consuming instructions. So things are just getting clogged up and performance is degrading because of that. Increasing overheads. David touched on this a little bit too. It's not free to simply instantiate a lot of processes and simply say, well, they'll execute when resources are available, right? Processes that are waiting, whether it's because of a recursive tree that's expanded beyond the limits of the machine or for whatever reason, consume resources, okay? And, this is a bad thing. In fact, the early work in the data flow machines from the 80s basically failed because, data flow is a very nice model and it exposes a lot of parallelism, but exposes too much. And you end up with simply consuming huge amounts of resources with waiting tasks, and the whole performance of the system degrades. Okay, so you do want to over-decompose a little bit. I don't want to scare you away. You don't want to minimize your parallelism. You do want to over-decompose slightly for the size of your machine, because that is a good way and an easiest way to improve for load balance. And load balance is a critical performance penalty if you don't get the load balances right. So you want to over-decompose slightly, but not too much. Is sort of the story here. Okay, and you certainly want to, you don't want to be scheduling all this stuff yourself and worrying about things, about the runtime or the operating system bottlenecks, and you don't want to be looking at, how the machine is changing over time, or how other processes are perhaps, interacting with with the availability of the processes for you. So you do want to rely on, the runtime systems and the operating systems to do a lot of this work for yourself in scheduling resources and in managing the resources that are available and dynamically adding and subtracting resources to your application, as they become available. And as Microsoft, we're spending a lot of time, and David covered a lot of the things that we're doing in his talk in order to provide a very dynamic, fine-grained runtime system to do the management and the scheduling of resources for you. And sort of the thing to always keep in your mind, you want to get this right to begin with, because the number of cores will be changing and will be increasing over time, and you want to be able to ride that wave without re-architecting your code and without spending large amounts of money to change the way you're doing things. And so, you really want to think about your problem, parallelize it to get enough parallelism to saturate the machines, give yourself a little bit more to do the load balancing, but you really want that the order of the parallelism, or how much of the parallelism you've exposed, really to be a factor of the problem size and the processor count, right? So you really want to be able to, write your program at a certain level where it will scale in general with the size of the problems that you want to compute and with the number of processors. Okay, so in the capability realm, there's sort of two ways to divide up problems. There's sort of the task parallel way to do it, and then there's the data parallel way to do it. And task parallelism, basically what you do is you have a problem, you recognize certain sort of similar operations you want to do, or certain similar types of components, large components of your application, and you basically write a task or a thread to do each one of those components, and then you schedule those on the cores of the resources you have, and they run in parallel, synchronizing and sending communications and values between them. So, particular, game distribution of work might be, in these 7 tasks, you have an audio part, you have some sort of user interface thread, you have a video thread, something that connects you maybe with the outside network so that you can play with a variety of external players. You have a thread that manages your avatars, one that manages the vehicles, another one that maybe manages the weapons. So, I mean, this is not, this is just for, example here, but sort of a way that you may take an application and sort of divide it up among sort of these large chunks or large tasks. And now you have your tasks, and you program each of these tasks with sequential code, and you've got, a certain distribution of work and a certain amount of parallelism. So the good and the bad of task parallelism is that the good is that I have fairly high-level chunks. They're sort of obvious in most cases. They're big chunks. So I do a lot of work, and I can amortize the cost of spawning of that work and the creation of the work. Also, my communication is fairly coarse-grained. I'm either sending large messages between these different tasks, or I'm sending few messages because there's not a lot of coordination at the highest level. Synchronization is also minimal. I don't have lots of little things all trying to coordinate to their own data. Each of the tasks, for the most part, works on its own data with few communication and synchronization points. The downside of that, though, is that I do have a small number of tasks, right? So this may not scale very well, and may not load balance very well, right? So it's probably the case that I'll need not only to program or design at that top level in terms of tasks, but I'll have to break down each of those sort of large tasks either into a large number of subtasks, or maybe exploit the data parallelism within each one of those tasks. So task parallelism is great. I like it. I've used it, but it does tend to sort of limit the number of things that I can do concurrently, and therefore limit the scalability I might have. It's also typically not a function of the problem size, right? It's really here's really a problem of the, sort of the components of a problem. Games probably won't have more tasks as they get more complicated, but they will want to have, more components, more weapons, more vehicles, better rendering for the number of pixels in the display and things like that. So the tasks will tend not to increase over time, but the sizes of the data which the tasks work on will tend to increase over time. So in data parallelism, here we think of applications not in terms of sort of the jobs they do, but in terms of sort of the elements they do. So if I have a graphics problem that I'm trying to do, I may think of all the pixels that I want to render. So regardless of what type of pixel it is, I'm doing a thread per pixel. I may also think of the number of triangles, for example, in a 3D model. So again, regardless of the type of triangle it is, I have a loop of some sort, which is simply executing over all the triangles in the application. In a game, I may have, for all elements of the game, regardless of whether it's a person, or it's an opponent, or it's a vehicle, or it's a weapon, just for all elements in the game, I want to do something. So this tends to generate lots of parallelism. Definitely scales with problem size. As the problem gets larger, I get more and more elements. And so it's easy to load balance, and it's easy to scale over time as my problem gets more complicated. It's also sort of, it's also very nice because it's just typically just loops, right? For all elements in the model, for all cells or whatever. So it tends to be fairly close to what the sequential code is, right? Most sequential codes is a series of loops. And so now if I want to parallelize that, maybe I can get away with just parallelizing each of the loops, and I'll be done with it, right? So that's sort of a nice thing, too. It does tend to push, conditionals inside those loops, right? If I'm doing something for all elements, once I go inside the body of that code for the element there, I may now have to decide, what type of element it is. And so I've pushed conditionals inside my loops. That can, of course, hurt software pipelining, hurt the use of vector instructions that some of the hardware now supports. And so that can be somewhat problematic and lower performance in that sense. Okay, so in the data parallel world, well, the task parallel world tends to sort of naturally break into the tasks that you have. The data parallel world can usually be split at many, many different levels, and deciding at what level to split the problem or to architect the problem can be critical. If I do it at too higher level, then I get more work per parallel invocation, but I may not scale well. So here are just some examples. If I have a grid problem of some sort, I could either parallelize for each of the subgrids in the model. I could parallelize for each of the planes in the model, or for each column, or even each cell in the model. As I increase the level of parallelism, of course, I potentially increase the level of communication and synchronization that I have to be able to support and amortize over the work. In a game, again, I could parallelize, again, for each element of the game, whether it's a person or a vehicle or a weapon or whatever. And if I'm in a graph-like problem, I could parallelize for every node in the problem or every link in the problem or whatever, okay? So again, there are many different levels in the data parallel world at which I can place the parallelism. And, once I've placed it, it can be very difficult then to sort of unravel that and undo it. So you really do need to think about, the right level at which to parallelize a data parallel application and, get that right for what you plan to do over the future and what the hardware increases will be. So here's just a simple example of this. Here's sequential matrix multiply. Simply this simple triply nested loop. For every the top level, for every row in the A matrix and every column in the B matrix, which is the second loop. Let's see if I can get this. So here's the the row loop. Here's the column loop, and then for every cell in that row and column, I simply do a multiply dot product. Dot product of A sub I k with bjk, and then I add it to the result matrix Cij. Okay. So this is what sequential matrix multiply might look like. And in the data parallel world, this is very simple to parallelize. With our extensions, I just need to slap a parallel.for in front of that first loop, and now I've got a parallel implementation of this matrix multiply. Okay. Now this works fine, right? It was very simple, and it works just fine. Except, when n is small, right? When n is small, all of a sudden, this doesn't scale very well, okay? And, if both n and m are small, then there's not much I can do. It's just a small problem. But, there are a lot of cases where n is small and m is very large, right? And there are problems where the size of n and m change, right? So what do I do, right? If I simply implement this as the parallel loop, I don't have something that scales very well. I have something that maybe sometimes performs well and sometimes performs very slowly depending on the problem. So this is not a particularly good solution. A better solution is to fuse those first two loops, the n and the m loop, since they both can be executed in parallel, and produce now an application in which the outermost loop is across n times m. So now I've got n squared parallelism, right? So now regardless of whether n is small or m is small, I'm going to get basically the same performance as long as one of them is large. Of course, if I do that, I've introduced a slight complication in that I've got to recompute the I and j values in order to pull out the right elements of A and B and add it into the right elements of C. So here I've taken a problem on the first case, which was very simple but may not scale well in all instances, and I've architected it now to improve the scalability of the problem. But I've complicated my code slightly in that I've had to recompute the values of I and j. Okay. There's, one more complication. If I go back, one of the things you want to do, of course, is you do want to limit the number of loads and stores you're doing because those go across, first of all, a critical resource in the machine, which is the network bandwidth, but also sort of over the slow link in the machine. Networks, data networks, memory networks are very slow. Processors are very fast, and so you want to stay in the processor as much as possible when you're writing parallel code. And in the innermost part of this loop, for every multiplication I'm doing, I'm basically adding into the Cij element. And so, I'm doing a write to Cij, and depending on the cache and who's writing and where and things like that, this could be pretty expensive. It could cause cache flushes and things like that. Now, most compilers would probably be able to optimize around this and come up with a better solution, but, not all compilers, and not all instances of a loop. So one of the things you do want to think about is minimizing the number of loads and stores you do in your innermost loops. And the simple way to do that is simply by declaring a scalar here, sum, adding into sum, that'll be now a register in any implementation, and then doing the single write at the end of the innermost loop. So again, you do want to optimize your innermost loops, your innermost, your finest threads to minimize the number of load stores they do, minimize the number of computations they do. It'll just improve your performance and improve your scalability. Okay. Here's another example of where, again, it looks like the data parallel implementation is very simple, but it does introduce some complexities. So data parallelism is a good model, and it's usually easy to convert a sequential code to a parallel code, but not everything is for free. So here's just a simple example. All I want to do is I have an array of integers, and I simply want to permute those values. Okay, so the easiest way to get a permutation of the array of integers that I have is simply to do some number of swaps on the arrays. And for every swap, I'm going to choose the ith element and a jth element, and I'm simply going to interchange them. Okay. So the sequential code is very easy, right? I simply have these 8 lines here or whatever. Okay. So in the parallel world, I can simply take the outermost loop and simply do the swaps in parallel now. So, I use our language extension here. I slap a parallel.for there. I now have a parallel loop, which will, scale with the number of swaps that I decide to do. Well, things aren't quite that easy because there's a potential here for race conditions and for deadlocks. Okay, I've got to make careful that the concurrent swaps that are occurring don't choose the same I and j values, right? Otherwise, I'll end up getting garbage. So the way I do that is I want to lock element I and element j for every one of the swaps so that, the swaps don't end up stepping on each other. So again, just getting a parallel loop with here was simple, but it's introduced the complexity here of having to do things safely. So the way... So if two swaps, if one swap, for example, chooses the same I, and then, the next random number comes out so that it chooses the next j, and it locks the I element first, it's going to sit there and spin forever trying to lock the jth element, which happens in this case to be the same element. Of course, that's a deadlock, right? So the way to avoid that is simply by including a conditional in the code, which says that if the I value and the j value I happen to come up with here, I'll simply continue and I won't do anything. The other problem, of course, is if I have two swaps, one chooses I and now locks I and now goes and chooses to lock j, and another swap has come in and chosen j, and so it's locked that one, and now it tries to lock I, and of course now these two things end up sitting there spinning forever because they've each locked their first element and they're waiting for the other one to be able to get out of their way so they can lock the second element. And the simple way to fix that is simply always to lock the lowest element first, and that way I can break that deadlock. So if I is less than j, then I'm going to swap I and j, right? So now I've always locked the lower indexed element first, and then I'll lock the next element next. Okay. So once I get my I and j values, I'll lock I, I'll lock j, and then I'll do the swap. Okay. So again, the parallel implementation here was simple, but I have to do the locking correctly, otherwise I end up with a problem. Okay. Now, maybe we can make this easier for you by using transactional memory, something that David touched on, right? So instead of having to worry about I and j and which one I lock first, maybe I can use a transaction, and in the transaction, I simply choose I and j, and I go and I swap I and j within a transaction construct, and as long as two swaps don't actually touch the same I and j value, as long as I don't touch the same value, the swaps will happen, and everything will be happy. So, I didn't have to worry about if I and j are the same or lock one early and lock one late. The transaction saves me a lot of time here. Okay, so I've been told I have to hurry up. So, okay, so One of the key things here to take away is that you really need to look at optimizing your code. You can't get away with just writing sort of sloppy code. Here's some things just to keep in mind. You always want to use the best parallel algorithm. If your algorithm is inherently sequential, it's not going to speed up. Use hardware accelerators. These are great, GPUs or whatever can make your problems run faster. Use special instructions like the SSE instructions that are available in the Intel hardware. Push parallelism out as far as possible so you make your work sizes large. Make your communication synchronization points fewer and far between. But again, you do want to over-decompose your problem slightly to improve load balance. You want to cut off recursion. David touched on that. You want to accumulate locally so that you're not, you minimize the number of loads and stores. Pre-allocate memory. Don't allocate memory in lots of objects inside of parallel loops. There's probably a bottleneck somewhere in the memory allocator, and that will eventually hurt your performance. Collapse and fuse your loops so that you get, again, bigger work grains and things like that. You use parallel data structures, okay? I mean, we're very customized to use things like queues and stacks and things like that. Linked lists, those are not parallel data structures, okay? They have single entry and single exit points. We can minimize those. We can optimize them for you. We can do whatever we want. But in the end, those data structures have a single entry and a single exit point, semantically, and at some point they're going to end up killing your performance. And finally, remove I/O from inside of parallel regions. So I had an example here with breadth-first search. Maybe I'll just do one of these examples just so you can see some of the things that we're providing you to make programming easier. So breadth-first search, the definition is fairly simple. I have a graph with nodes and edges, V and E, and I have a special node S and a special node T, and I just want to decide whether there's a path from S to T, right? So I have a source and a sink. Two common solutions. One is to maintain a horizon of active nodes or reached nodes. And so I have an outer parallel loop that for each horizon, it simply computes the neighbors of all the elements on that horizon. That expands the search, and basically the user manages this array of this horizon array. And the other simpler implementation of recursive recursion. I start at the source. I go to each of its neighbors in a recursive manner. Each of those neighbors goes to their neighbors, and eventually one of them reaches the sink node, and then the whole thing can quit. Okay. The recursive implementation is much easier to implement. Basically, you're relying on the system to manage your horizon list, as it would be, or the things that have been activated or reached. David had a nice example in his talk about a recursive tree. Okay. So I'm going to. So the horizon method starts at S, right? That goes and creates now a list of some sort of the neighbors of S, so 1, 3, and 5. Each of those nodes now goes out to their neighbors, and so I get a list of 2, 4, 6, 8. That's the new horizon. And then each of those goes to unvisited neighbors. I get a list of 7, 9, and then the sink node T. At that point, I want to quit. Okay. All right. So here's the code for the horizon method. The key thing here is, of course, is to quit, right? And also to be able to maintain this list of this horizon, right? Typically, how you do that is simply by managing two queues, right? You take the things out of the current horizon and put new things into the new horizon. We've simplified that by this blocking collection, which allows you basically to declare a type in which we will manage the simultaneous extraction and insertion of nodes into this queue. Okay, and now I can simply do a parallel for each element of the horizon, and this simply will execute until either the horizon is empty and no one's added new elements, in which case I haven't found the sink, or I can use this horizon complete adding when someone does find the sink. Okay, and what that will do will be to set a signal for all the threads that are consuming elements out of this horizon that they should quit. Okay. So I have here simply simplified the horizon method where I've provided you a type, right, a blocking collection, which allows for the automatic management of things being added to a queue, as it would be, and extracted from a queue. And that will simply be continuing to process until there's nothing in the queue or someone signals completion. So that's good. Okay, I'll skip that slide. Okay, the recursive method is pretty simple. I start at S, right? Then I recursively go to all the neighbors of S, so that's 1, 3, 5. Each of those threads now recursively goes to its neighbors, so maybe 1 goes to 2, 3 goes to 4, 6, and 8. 5 is slow, so it goes to nobody. 4 goes to 9, and 8 goes to 7 and T. And now I want to quit. So the problem here is, of course, I've got all these other threads. I got a thread at 2, I got a thread at 9, I got a thread at 7. Someone's reached T, I want to sort of stop them all. So how do I stop them all? Oops, wait, I'm going the wrong way. Okay. So in the recursive method here, I'd have a public method and a private method. And the public method would basically set up this cancellation token source found, and that's a way that I can set up a global variable as it would be and set a signal for all the active threads that are participating in this recursive tree that's unfolding to quit. Okay. And if I find the sync, then someone will have set this cancellation request token to be true, and so I can simply return that as the result of my breadth first search. So again, we've provided you a very easy way to implement recursive searches and to kill everybody when the goal has been reached. Okay. So if I recursively call this private breadth first search method and the cancellation flag has been set, I'll return, because I'll just kill myself, right? There's nothing for me to do. If I find the sync, I'll set found to cancel to signal everybody that they should quit. And if not, I'll simply recursively call breadth first search. Okay. So again, we've given you a very easy way to implement recursive parallelism, and in particular, an easy way to cancel the recursion when necessary. And David showed you how we implement recursion and how we minimize the resource contention and the resource use in recursion in his previous slide. And so we've provided you with a very efficient, very easy way to implement recursive parallelism, and it's a very powerful method. In our system, the recursive method here would probably execute better than the horizon method, and there are very few parallel systems in which that's actually true. All the other parallel systems I've ever programmed, the horizon method always runs better than the recursive method, basically due to the overhead in recursion, the use of unrealized resources, and then expensive or an inability to kill actually the recursion once the sync is found. Okay, so in summary, and I'll turn things over to Jerry. I've probably gone a little long, and I apologize. So in summary, find the best parallel algorithm to start with. The literature, we've got a long, probably 100-year literature on parallel algorithms and parallel complexity. You should start there. Find the best parallel algorithm for what you want to do, and then think about how to implement that. Find the right level of parallelism. You don't want to be re-architecting your code every 2 years as the number of cores increases. So think about the size of the problems you want to run in the future. Think about what the size of the machines might be, and program at a level which is of the order of the problem. And so as you make your problem larger and more complex, it'll scale naturally. Think data parallel first. I find that sort of the easiest way to think about things. Task parallelism is fine and great, but it can be sort of limiting in scalability. Use parallel data structure. Try to use things like trees and graphs, dictionaries, arrays, vectors. Those are all parallel data structures with multiple entry and exit points. Queues and stacks aren't, so be careful. Minimize shared data and synchronization, and just optimize, optimize, and optimize. The more you can optimize, cleaner your code will be, easier it will be for the compiler. Less spaghetti coded will simply just run better and scale better. And again, the big takeaway is that bad sequential code will run faster on a faster processor. That lunch is over, and you really do need to think about running clean and efficient parallel codes. Okay, so there's our website, and I'll turn things over to Jerry. And sorry, I went a little long.
Hello? Okay, good. Thank you. Well, good morning, and I'm delighted to be able to speak with you this morning. I'm from Intel Microprocessor Research. I'll talk to you today about some of the things that John has picked up on and earlier speakers as well. But the area that I'll be focusing on is something called connected visual computing, which is a major area for us, an area that we're focusing a lot of effort on, particularly in the research area, and also an area that is scaring the heck out of our hardware architects and platform architects as well. So I'll touch on some of the demands that these workloads are driving. And before I go on, though, I do want to thank our Microsoft friends for inviting me to speak here this morning. It's quite an honor to come to PDC. Thank you. Okay, so let's start off at kind of not even the 30,000-foot view, but I don't know, a million-foot view. It appears as though there are some pretty major trends in the Internet. Certainly visual computing is one of them, and I'll be talking about that in quite a bit of detail. But visual computing really is sort of photorealism, ray tracing of images. That is the way that light leaves a source, is refracted, reflected as it comes to our eye. Images generated using ray tracing have a tremendous amount of realism to them. Obviously, user-generated content is exploding. We've all seen many plots of exponential curves of storage, online storage associated with YouTube and other sort of social networking sites. Social networking itself is creating a huge network demand and requirement for transportable content between various websites and storage. Finally, people expect to take their mobile platforms with them. So whether it's a handheld device or a notebook or an embedded processor that's in your car dashboard, mobile computing is growing dramatically, and form factors are obviously proliferating at the same time. And then finally, all those devices need to be connected somehow. We can't do social networking. We can't upload content if we don't have a pipe to a storage facility somehow. So Wi-Fi, WiMAX, other kinds of connectivity or 3G, et cetera, are all growing as well. So really, truly, it is driving towards a connected, graphically intensive world. So what is visual computing? It is really more than just three-dimensional kind of views. So the picture on the left is a ray-traced image. Again, the notion here is this mimics the way that light propagates and that we see. So light rays emanate from a source. They bounce, they reflect, they're absorbed by various textures and such. They approach our eye, and the way that those light beams propagate really creates an image that is incredibly lifelike. Searching has gone beyond text tags and such. We'd love to do intelligent image searches. Find a picture of my grandmother, find a picture of my grandmother when she's happy. Those are quite sophisticated things to consider, as you obviously well know. Also decomposing those images into body parts. For example, here is some software that we have to look at how, in this case, a soccer player with left arm, right arm, where the ball is, where the head is, et cetera, that is used to look at kind of strategies in a game. Computer vision. The example here is a dashboard view of a car driving down the street, automatically using visual cues to find people, cars, threats, things like that. All of these things in real time have to happen and create a tremendous compute load. Physics in games. The average 12-year-old who plays a game really doesn't necessarily understand Newton's laws, but they know it when they see it. They play, they crash, they fall, they know what momentum conservation is. And so if the games mimic that, they're much more lifelike, they're much more real. But again, that's a pretty heavy compute load to calculate the dynamics of multi-body collisions, which is elastic, which is inelastic, et cetera. Finally, the way that we articulate faces of creatures, in this case a human, but it doesn't have to be. How do we do that? We have some software that we're working on in research that actually uses musculature and physiology to move faces and eyebrows and things like that in a way that's very natural. And again, our DNA is wired in such a way that we do recognize when a smile is real or when it's not. So all of these things speak to things that look real, that behave real, and that they absolutely feel real to us. So, but again, the point here is that these use every single flop that's available and then some. So if we talk about visual computing as sort of a genre of generating images and such, obviously the point here is that these things have to be connected. So social networking, collaboration, online gaming, etc. These are all aspects of this. And there's a couple different major ways that we kind of bin these things. One is what we call augmented reality, that is sort of enhancing the real world that we see around us by inserting digital images, overlaying them in various ways. So you see some earth mapping examples there. Augmented reality is another thing that might be useful for a handheld device as you're moving around in a tourist situation. And then finally, sort of the total immersion into digital worlds, MMORPGs, virtual worlds, etc. These are all examples of environments that are obviously compute constructs that people want to immerse themselves into. So connectivity is key here, and that is between the real world data that's available at various places on the internet, and then finally to the individuals themselves. And this connectivity is really a key aspect of this, and we'll touch on this. So this in these last two slides, this was sort of the whole notion of connected visual computing, which I'll be talking about now in greater detail. I'm just going to breeze through some of these examples. There's no need to discuss them in any real detail. Certainly simulated environments, virtual worlds, Second Life. I'll be showing some data where we've looked at how Second Life as a client application and server application partition across the network compared to, say, something like an MMORPG, a World of Warcraft kind of thing. So it's not just all fuzzy slides. There's actually some data here. And we'll touch on that. Certainly visualization of data, whether it's a simulation instead of sort of dry plots of wind speeds and things like that, but an animated simulation of huge dust storms that occur in arid regions. Outbreak CDC has been using visualizing, and we've seen it all in the movies many times now, of outbreaks of various things. Virtual medicine. I was going to make a comment here that I'll restrain myself. But anyway, you know, the notion of something like a virtual colonoscopy for training. This is a useful, certainly a useful thing that the medical domain is looking at too. So there really are some very good applications now that are graphically intensive that look at how we visualize data that help us communicate, understand, and sort of look for the trends that are more subtle. Collaborative environments, it's not just for games. There are a number of startups pushing sort of virtual team rooms where, you know, we're all facing some difficulties these days in travel due to potentially economic reasons, but nonetheless, the ability to have real sort of interactions in virtual team rooms where people can gesture and point to things and hold up three-dimensional models of such is really kind of a new sort of element that is quite useful to sort of the work in an enterprise environment. And then finally, the way we share information in terms of how ideas are organized and things like that, there's another dimension there we can use as well. Augmented reality, I mentioned earlier. Obviously, the linking of GPS data is useful to pull up interesting facts, dependent, of course, on where you are. So contextual aware there is important. Recognizing creatures. So here's a little bug. This handheld device then will go out and find information about this particular bug. Instruction, you can imagine the overlay of a complicated repair process on a complicated piece of equipment, where a virtual hand comes in with a wrench of a certain size, indicates to the worker where they should do something. This can, of course, cut down on training time, mistakes, etc. And then finally, those of you who might have attended the Olympics recently, there was a huge challenge just getting around in Beijing, how to deal with for those of us that cannot read Chinese characters, what are the street signs and stuff like that. So sort of automatic translation is a useful thing as well. So there are quite a bit of variance on this augmented reality, but again, this is another aspect of visual computing that we focus on. So that's the end of kind of the the pretty pictures here. The point, though, is to make it clear that there are some very compelling applications out there, and that now the challenge is how do we enable them, both from a software and hardware perspective. In the case of the platform, certainly and I'll show you some data in a little bit here, certainly server and client demands are increased dramatically. The throughput requirements are quite a bit higher than sort of the legacy apps. They rely very much more on network connectivity. So packet accelerators, fixed function engines, encode decode engines, things like that are all extremely useful in helping to enable very high interconnect bandwidth. All of this has an overlay of energy efficiency on it, which is a vector that's going exactly in the wrong direction in terms of these things. It takes so many picojoules to execute a command or to transfer a bit. And if there's more of those that have to be done, then how do we reconcile with the fact that people want to take smaller, more capable devices and have limited battery life? How do you deal with those opposing forces? So the optimization point is clearly not going to make everybody happy, and there's no way around that. Distributed computing, we talked about a mobile environment where people are taking their handheld devices, moving around, going different places. Code has to move from one platform to another. You're playing a game at home, you get in your handheld, you get on the train, you want to just keep playing that game or stay in that virtual world. Obviously the screen size, resolution changes, all that sort of stuff. And that speaks to this notion of client diversity. And then, of course, then how do you program such a thing that would allow that kind of flexibility? Visual content itself. Again, we're talking about user-generated content. But then we don't want to create a fancy avatar and spend a lot of time doing that and then not be able to move it from one environment to another. Right now, that's a major challenge. So could we take our World of Warcraft ogre and drop it into Second Life and do some interesting rampaging? You can't do that today, and why not? So that's something that likely will have to change. And then we talked quite a bit about mobility, and this notion of sensor integration is a new one here. And that is not just GPS, but also pressure, temperature, other kinds of accelerometers, other things that are useful in terms of collecting information in the environment and helping you with ambient light sensors to help you with contextual aware sort of applications. So as I said earlier, yes, these things are all really cool. They drive the richness is something very compelling, but it drives a huge level of complexity in terms of greater number of users that are interacting, the complexities of the scenes, the number of objects that have to be dealt with, and then finally each of these objects have to be rendered to a fairly high level of realism for them to be really sort of deliver the user experience that we're looking for. So it really is quite a challenge to provide that kind of sort of richness. So here's some data where we looked carefully at World of Warcraft and Second Life. And these are, again, not to ding them in any way. These are just examples of MMORPGs or virtual worlds. And we looked at them both from the server side, the client side, and finally what sort of network bandwidth was driven. And essentially, on the server side, the server is really consumed 75% of the time just serving this application to the end user. So there's very little time for anything else. Similarly, on the client side, those of you who do run around in Second Life, you realize you can do very little else but Second Life on most platforms. So about 65% of the time is completely consumed with just a few threads that are associated with the client side of Second Life. On the server side, if we go across near the top, the number of clients per server scale actually quite reasonably for World of Warcraft. Several thousand can be simultaneously dealt with on a single server, whereas in Second Life it's much closer to a few hundred. So really there is a dramatic difference then in how the server-side software can be implemented across a data center or data farm. You can imagine how this affects the business model for virtual worlds. It makes it quite difficult when the amount of hardware you need is just significantly higher. On the client side, we looked at just sort of three representative things, sort of just normal 2D websites, in this case Google Earth. It could be any sort of mapping software as well. And then again, Second Life. And for the most part, and there's quite a bit of data here collected over time, but for the most part, for most sort of web kind of stuff, about 20% of the CPU is really used. But in the case of Second Life, as I said earlier, about 70% is totally consumed with just running that client. And the graphics is not just on the CPU side, but the GPU is also incredibly busy with anywhere from 35 to 75% consumed. So really, the point here is, yes, these things are cool, but they really extract a toll on the platform. So that's something to definitely keep in mind. On the network side, there's a dramatic difference between these things. And in the case of Second Life, the problem is really on the server side to the client. There's relatively little information that goes up from the client. There's at least a 100x or certainly a 10x difference between what goes down from the server. And most of this has to do with what's cached and uncached. So in other words, if you go to Second Life and you happen to visit someplace where you visited fairly recently, on the disk, a lot of the information is there. Rendering is relatively straightforward, and therefore that in that cached case, that's really not quite too much of a load. But of course, who wants to keep going to the same place over and over? So the problem is there's a tremendous amount of additional information that almost always has to come from the server. So therefore, there's a much bigger load on the downstream bandwidth pipe. In addition, just user-generated content. When most people are drawing images, just unlike gaming developers, they don't really pay attention to how hard it is to render an image. They just want to make the picture. So there's no optimization at all on the way that people generate their own little domiciles or furniture or whatever that's done in Second Life. And so therefore, the user-generated content itself extracts a heavy load. And of course, all of that is unique. All of that has to go up to the server. It has to pay attention to all of it and render it individually and faithfully. So really, there's a very big demand just in these virtual worlds alone on the way the platforms have to deal with them. So I've tried to make the case that in terms of scaling performance for parallelism, there are really two vectors that we have to pay attention to. One is just raw throughput instructions executed per second. The other one is the size of the data sets. What good would tera instructions be if you were only being able to probe or deal with very small data set sizes? So both of these vectors have to increase simultaneously, and there is a major challenge. We've looked at these, a lot of these workloads coming from the entertainment industry, financial analytics, Wall Street, et cetera. And given the current situation, there's even more work being done there these days in terms of projecting futures. Personal media creation and management, again, this audience is probably the most up-to-date on this, that we have tremendous amount of digital content creation on our own hard disks at home that have to be dealt with and searched. And finally, of course, I mentioned health already as another area. So there's some very strong sort of application spaces for us to consider. So how do these things scale? We've looked at, again, a very large breadth of them. I'll start off at the top. There's two kinds of computational sort of dynamics or fluid dynamics applied here. One is called production. The other one is called game. Production is something that a professional content creation house would do for a feature-length movie. Gaming is obviously fluid mechanics or dynamics of bodies, rigid body dynamics that are suitable for a game and somewhat less quality. Sports analysis, I showed a soccer player that was sort of finding left and right arms and legs and such. Home video editing, ray tracing, I mentioned that as a technique for generating very lifelike images. Human body tracker, portfolio management, et cetera. So there's there's at least 3 times this many kernels and applications that we've looked at. But the message here is that for the most part, these are sort of data parallel in nature. And if you were paying attention to John earlier, you know the difference between that and task level parallelism. And also you'll see that from a scalability perspective, a lot of these actually scale quite well to 64 core, and something like ray tracing scales extremely well to even thousands of core. So there's really inherently little sort of encumbrance with regard to being able to parallelize some of these things. The problem, of course, is that memory bandwidth or other platform limitations will get you long before you'll find in the case like of ray tracing, for example, long before the code will get you. So enabling sort of on the order of half a byte per flop or 3.3 bytes per flop is a huge power and resource challenge, and one that the memory vendors are starting to wake up to as well. So what are techniques that we can use to kind of help deal with some of these challenges? One of them is sort of something we call, there's two products that Intel has at least that are available now, and one of them is a thread checker that sort of helps with how code can be, these are both for optimization. TBB or thread building blocks is another one where you can look at threads and see where they're being choked and how information is flowing between them. It allows for quite a bit of optimization. So these are quite useful tools to consider. Also, just in the case of gaming, we've done some work in terms of looking how, say, for example, the Nehalem timeframe, which is now, how do we partition threads and at the same time make use of certain gaming engines that are available, like Havoc and others, to inject physics and stuff. And you know, the target, of course, is when we have an 8-threaded machine to fully load each of those core. CT is another very promising technology that we're working on very hard. And this allows sort of the automatic parallelization of code. And again, I really say that in quotes. It is, you know, exactly as John said, the thing to do is think about parallelism right at the start as opposed to hoping to take advantage of it later on. But there is a lot of legacy code out there, and there are some tools that, you know, for the more traditional programmer that they can take advantage of. And CT is a good runtime environment to try to deal with that. Also, the other problem we see is in the future, core counts and things like that will vary between machines. GPU content, CPU content will vary. It would be very difficult for the programmer necessarily to be aware of all the hardware resources on every single platform that they're likely to dump their application to. So is there another way to deal with that so that the code can then be optimally partitioned across a variety of hardware platforms? And that's where some of these runtime approaches seem to be fairly promising. So I'm kind of heading towards a slow summary here. So in terms of distributed computing, you know, I've tried to touch on the fact that really it is a very rich environment, both in content, in applications, and also very much so in the hardware and the interconnects that are required. So large data centers that are connected by high-speed optical links, wireless, on the other end, wireless clients that are proliferating now in terms of different form factors. The line between PDA, cell phone, and MID are sort of blurring, and that will continue to be the case. Embedded CPUs in various devices are also ballooning as well. So that's an issue. And the cloud as a resource for doing some heavy-duty computing that is then dumped to these handheld devices and displayed to the end user is something clearly of interest. In home, the workloads have really blossomed in terms of gaming, media processing. Those of you who have tried to transcode things realize that that's actually quite a long and cumbersome process as well. So really, truly, it's a very rich environment. I'm not sure, as I look at this slide, I'm not sure if we're implying that they're extraterrestrials doing CVC as well with these additional worlds up in the corner. But anyway, truly it is a connected environment for sure. Let's see. So, you know, just in order to enable this thing, there really are a number of core building blocks that need to be dealt with. One of them is sort of the service providers themselves in terms of what sort of infrastructure is there, what kind of asset tracking and revenue tracking will be there. The platforms themselves that are driving these things. We're talking about third-party software, so-called middleware, to do a lot of this work. And then finally, the hardware and the platforms themselves that are resident at the end user's hands. One analogy we make is, of course, we look back in time and say, what can we learn? And certainly, HTML provided kind of a way to break some of the walled gardens, and we say that in quotes, that existed some time ago. For example, what Prodigy or AOL or others had. And by sort of applying sort of this notion of open standards and common approaches to sort of rendering web pages, that allowed a greater proliferation. And we think probably in the case of the CVC thing, it's going to follow a similar path, that there will be companies that specialize in support services, those that provide tools for user input or gaming physics or things like that. And then presentation, sort of what happens at the end, how are things rendered, and how is information collected from the end user. So we see sort of lots of opportunities for partitioning this. And if you put these things together, you can imagine that you would end up with sort of in Tomorrowland, sort of this horizontal view where things are sort of broken up into layers that are interoperable and allow for different sort of revenue models for different companies to focus on different pieces of this. At this point in time, that doesn't exist. But in order for this stuff really to proliferate, we do believe that there's going to have to be a flattening and a commonality of data structures. OpenSim is an example of that in the virtual world environment. I already mentioned that visual content needs to be interoperable. You'd love to be able to take avatars and move them around, or furniture that you've created. And SketchUp and other things are starting to emerge to allow that. I think in terms of generating content ourselves, here's a simple application where you can generate a face, and simply by sliders you can kind of change the conformation of the face. These sorts of things are going to be more commonplace for creating more sort of individual or more expressive avatars that then, of course, have to be animated appropriately as well. There we go. So really, we have within Intel a tremendous breadth of research going on to look at platform optimizations, to look at how we might build scalable apps, how they are going to be distributed across a variety of platforms. Content creation, how do we do that better? How do we build platforms that support that in a much more efficient way? And then obviously the mobility aspect and WiMAX and Wi-Fi and all that has to be incorporated in there as well. So to summarize, so we have a few minutes for Q&A. Really, we do believe that these CVC apps really do provide a very compelling user experience. I've tried to be sort of balanced, though, and say, yes, these are neat, but at the same time, they really do push us very hard on the platform to be able to provide the sort of capabilities that are required, both on the hardware and the software layer. But the story's not all bleak. We've done quite a bit of work in research trying to do some pathfinding here, and actually the results look pretty good. So in general, we're quite optimistic that these things can move forward, and that the user will have a significantly different experience in the next several years. Okay. So thank you.